Welcome back, and in this video we are going to continue where we left off in the previous video and talk a little bit more about the linear programming problem. What does it mean to solve a linear programming problem, and so on. Okay, so recall, here's what a linear programming problem looks like. Okay, and the goal is to take decision variables x1 through xn, okay, and let's formally make these decision variables real valued variables. So x1 is a real value, x2 is a real number, and xn is a real number. And this is really important. If you understood a linear program, then it's also needs to be understood that the variables that we are talking about are real valued variables. Okay, if they are integer valued variables, then the whole nature of the problem completely changes. Okay, all right, so we are maximizing a linear objective function. Okay, we are going to do that, and we are going to subject it to a bunch of linear inequality constraints. The constraints are going to be linear inequalities. They can be less than equal to, greater than equal to, or equal to, but in this case we will keep things simple and we will keep everything less than equal to, and Shalom will show you why that doesn't lose any generality. Great. So if that's understood, then let's look at the feasible region of a linear program. So the feasible region is formed by the constraints. So you temporarily forget the objective and just look at the constraints. So every constraint, a1x1 plus a12x2 plus dot 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 a1n xn less than equal to b1 forms a straight line with everything on one side, depending on whether this is a less than equal to or a greater than equal to. It's everything to one side of a straight line, and in higher dimensions it's everything to one side of a hyperplane. Such a region is called, in mathematics, it's called a half space. Okay, so and likewise every constraint ak1x1 plus ak2x2 and akn gives rise to another half space. And overall, you have a region that's bounded by half spaces, and the name for this in mathematics is it's called a polyhedron. Okay, poly means many, and hedron means faces, as in the faces of a geometric solid. Okay, so we have an n-dimensional polyhedron if the original problem has n decision variables. Okay, and since x1 and x2 are all real valued, every point inside this is a feasible point of the linear program, and the entire region is called the feasible region of the linear program. Okay, so with this terminology established, what does the objective function mean? So here again is the linear program, here again is the feasible region, and let's look at what the objective function means. So first of all, we can look at what are called the level sets of the objective function. Okay, what is a level set? Well, let's take this entire function c1x1 plus c2x2 to cnxn, and let's equate it to some value z0. Now if you do that, then you get a straight line, and this straight line is called the level set. It's called the z0 level set of the objective function. So every point here achieves an objective value of z0. That's another way of looking at it. Okay, likewise, you can increase z0 and consider the level set for z1. Okay, for z1. Now if z1 is strictly greater than z0, then every point here, let's call a point y1 through yn, let's call a point here x1 through xn, then every point from y1 through yn is strictly better than a point from x1 through xn. Why is that? Because it achieves a larger value of the objective function, and we are interested in maximizing the objective function. So what's the answer? The answer is really this. You're trying to move this family of hyperplanes corresponding to the level sets of the objective function in some direction that corresponds to an increase until you get to a point where it cannot be increased anymore. Move it anymore and it completely leaves the feasible region. Its intersection with the feasible region becomes empty. And if such a level set can be found, then you call it the optimal value or the optimal objective value. And this point where it touches, one of the points where it touches, it could be touching at many points, is the optimal solution. Okay, so here the optimal solution is unique. In some cases, it may not be unique. So take an example of a rectangle where our objective function is moving in this direction. So this is the level set, and this is the increasing direction. So the final answer will be like this, where an entire set of points are going to be optimal. So it doesn't have to be a single point, but in many cases, you can expect it to be a single point. Excellent. So there are three outcomes of a linear program. One is that at least one optimal solution exists, or many optimal solutions exist. The objective function is unbounded. That's an outcome 2. And the outcome 3 is the feasible region is empty. So outcome 1 looks like this. So you have the feasible region, and you have your objective direction, and they increase in this sense. And you find a point where your objective is maximized. So this is optimal. And if this happens, this is the happy situation, and this is the situation we saw in the previous slide. The other possibility is that the objective is unbounded, and we will see an example in the very next slide. But here the objective just extends infinitely in some direction, and that happens to be the direction where we are trying to maximize. So the objective goes up in this direction, and in this case there is no possible maximum, which means any value you can think of can be achieved and exceeded, and therefore we say the objective function is unbounded. The third possibility is that we somehow make the constraints contradict each other and the feasible region is empty. Once again, an example will be provided 2 slides from now. Okay, so let's take an example of an unbounded problem. In this case, we are maximizing x. So the objective function's level sets look like this. So these are the level sets for x equals c for some constant c, and it increases in this direction. Okay. Now let's look at the feasible region. So it says x greater than equal to 0. That's everything to the right of the y-axis. Y greater than equal to 0. Everything above the x-axis. And x plus y greater than equal to 1. Everything above this line x plus y. So therefore you have these 3 sides that bound your feasible region, which extends infinitely in these 2 directions. But unfortunately, this direction is also the direction in which your objective function moves. So therefore, if you think of any value of x, let's say 10 to the 6, I can think of x equals 10 to the 6 plus 1, and if this is achievable, then this is also achievable. Maybe x equals 10 to the 12 is achievable, x equals 10 to the 99 is achievable. So any value you can think of is achievable, and therefore a linear programming solver would give you an answer of plus infinity being the largest value of x possible. In MATLAB, you might get something like INF. Okay. Most linear programming solvers will have a way of identifying this and signaling this, because this happens sometimes. The other issue is when the constraints contradict each other, okay, and therefore the feasible region is just empty. Okay. In this case, let's take an example. You're maximizing x such that x is greater than equal to 0, x plus y is greater than equal to 1, okay, and x plus y is also less than equal to half. Now you can ask, how can I find an x comma y that at the same time is greater than equal to 1 and at the same time is less than equal to half? That sounds contradictory and is contradictory. So therefore the feasible region is empty, and the problem is called infeasible. Okay, so there is no real answer. Most solvers will signal that your problem is infeasible and will tell you that they can't find an answer. So it's good to remember that infeasibility can happen. And here the infeasibility is due to a trivial contradiction with 2 constraints. Sometimes it can be really subtle, and we'll see examples of some subtle infeasibilities as we move forward in this course. Great. So what does solving a linear program do then? A solver has to identify which of these 3 cases is happening. Is it infeasible? Is it unbounded? If not, is it feasible and bounded? Yes. Then find an optimal solution in that case. Okay. So in these 3 cases, only one case will get you an actual answer. The other 2 cases will simply get you a complaint or an answer of minus infinity or plus infinity, depending on what solvers you're using. Okay. And let it not be understood. So it's very important to understand that feasibility is often expected. This case is often expected, feasibility and boundedness. But there are many important problems where infeasible or unbounded also means something. And problems like this often arise in my discipline, for example, in program analysis or reasoning about programs. The linear programs you get there are very likely infeasible or unbounded. And it's very important that your solver identifies all these three cases carefully, or else it's not doing a full job of solving the program. Okay? And if it's optimal, then you print the optimal solution. In these two cases, there is not much to print. Okay, so the other thing to note is that multiple optimal solutions are possible. And as an example, think of this problem: maximize x such that x is greater than equal to 2 and x is less than equal to 3. But let's also add a y. Y is greater than equal to 2 and y is less than equal to 3. Okay? In this case, the maximum value of x is 3, but any value of y from 2 to 3 achieves this maximum solution. So if you want to draw a picture, your feasible region looks like this, and your objective is being maximized in this direction. And you can see that it doesn't touch the feasible region at one point, it touches the feasible region for an entire line segment. And there are infinitely many possible optimal solutions. Any value here is optimum. So, but that's okay. We can just print one of them, and that's enough. All right. So the next lecture, in the next video, I'm going to give you a small flavor of what linear programming algorithms are, and a little bit of history of linear programming. It's not going to be a professional history of linear programming. It's just going to be a very short and concise history of linear programming algorithms, and some flavor of what these algorithms look like, what do they do, before we dive into more details of linear programming. Thank you, and I will see you in the next video.